Today we're going to talk about double integrals in polar coordinates. I look at the material. I'm deciding not going to derive the formula in using their ideas. Actually, I want to talk about substitution for double integrals. Actually, this is just substitution. Okay. And then, yeah, we consider, for example, we have a domain here, right, D, okay, in the XY plane. Okay, and then have another domain I called use a different variable, okay, and it's U and the V. And that's a D plane, okay. Now suppose we have a map, send it from here to here. Okay, that map is given by the following formula. X is a function for U and the V, Y is a function U and the V. Okay, if you can figure out this, then the integral, here's a function defined out here, okay? So, but if we compose it with, yeah, so this is a function, right? The function actually is defined on the domain. So if we combine, yeah, this is a composition of two functions. The function was a map. So this, you get a function U and the V, okay? So the double integral here, okay? So double integral here, let's use the XY, yeah, let's use the XY variable. Yeah, it's more important which variable we're talking about, yeah? Okay. And can be translated to a double integral of a D bar, right? And then this function here now is a function U and the V. Okay, but there should be something additional here. So that additional stuff I want to talk about. Here, D bar. Okay, D bar is it's an area element with respect to U and the V. Okay, that's called XY, that's called the U and V. This is a so-called Jacobian, right? Now, this is an additional term, shows up. Okay. This is very similar to the one we use in, this is called substitution in two-dimension case, okay? And very similar to the one-dimensional case when the function is one variable, okay? If the function, before I talk about this, okay, let me give you, so let me give you the determinant first, okay? This is a, yeah, this is a determinant of partial derivative okay, you have 4 partial derivatives. So you get the determinant, the absolute value of the determinant. Okay, so this is a, let me erase this. Okay, this is a determinant. Okay, and then you take absolute value. Okay, so let's okay, so let's take a look at the one compared to the one-dimension case. The one-dimension case, if we have a function defined on A and B, right? Here's a function f of x. So you have an integral of A and B f of x, right? Now, if we have another, if we use a substitution, this is A bar and B bar, okay? And this is that's U, okay? Then, yeah, Yeah, we can use different parameters, fine. Okay, so u, okay, so x is x of u, right? Remember, we have the integral from a bar and b bar, and here f x of u, right? But we also have the so-called derivative of this. Right now, you only have one single function, so just a derivative. Okay. 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 It's very similar to this case, but here it's only one single variable, so so you have just the derivative of this function. Okay. Okay, so this is a slight difference. And now, there, yeah. So, but in with the two variables, okay, then you get four partial derivatives, and then you have to, yeah, put together actually become a determinant here. Okay, so now let's take a look at a special case. Okay, the special case is the so-called polar coordinate. Polar coordinates. So you have the map. So usually you have something looks like that here. That's a D. Yeah. Okay. Then you have the polar coordinates. It's going to be I and the theta. Okay. Okay. So this is another map. Moving to here. Okay. So the map is x equals r cosine theta, y equals r sine theta. Okay. Using that, okay. So here's the function fxy, right? All I need is to compute the determinant. Okay. This is a determinant of the matrix. Okay. So the partial derivative of x with respect to r, partial derivative of x with respect to theta. Here's with respect to r, with respect to theta. Okay. Now, sometimes they just use two vertical bars for means the determinant. Okay. This means the matrix. Okay. So let's find the derivative. Okay, this is cosine theta, negative r sine theta, and that will be sine theta. That will be r cosine theta. When you do when you compute the determinant, you get r cosine square theta minus negative r sine square theta. So you end up with r, because cosine square theta plus sine square theta equals 1. Okay, that's all we need. Okay, based on the above.
Professor, do you mind going through that calculation? It's been a minute since I've done determinants. So do you mind?
Oh, you forgot the formula for determinant? Yeah.
It's been a minute, yeah.
Yeah. So determinant is like that, as a cross product. Okay. This on this diagonal is the product minus the product of two numbers on this diagonal. So if we have a and a b, c and a d, the determinant of this by the formula is ad, okay, and the minus cd, cb, okay. Yeah, that's a called determinant. All right. Okay. So now you get this, right? So now when you apply the above formula, the question is we have to know what is d bar, right? It depends, right? So we have to, this is the difficult part, we have to figure out the part. So now d is the image of d bar, okay? So here x will be replaced r cosine theta, y is replaced by r theta. And here the determinant is just d, okay? That will be d bar, okay? D bar. So if you can express now, if you figured out the domain for r theta, then you can use the iterative integrals. Okay, at this moment, I just write it in this way. Okay, So if in particular, usually a d bar, you will get, usually, okay, d bar is given by this something like that. Okay, theta is between alpha and the beta, and I is between h1 theta, h2 theta. Now, what does that mean? That means here's r and here's a theta. Okay, so that means you have a r is between, yeah. So you have something like that. This is alpha, that's the beta. Okay, so this is a kind of a domain you usually get. Okay, so if we get a domain like that, then the double integral will be, how do you evaluate it? You have to take an arbitrary theta here and look at the horizontal line. Okay, so this d bar, this that when you're trying to evaluate, and that is going to be alpha theta is outside, and this r is between for fixed theta, right? I is going to be between those two numbers. So h1 theta, h2 theta, okay, and that is going to be f r cosine theta, r sine theta, and then r d r. Okay, so this is how do we get? Okay, that's the only way, if these expressed in this form, that is the only iterative integral you can use to evaluate this double integral. Okay, so let's take a look at some examples, and then we. Yeah. Sometimes, have we heard about the formula for the volume, right? For the ball, right? And now we can use that calculus to prove that. Okay, good. Where's my screen? That way. Okay. Okay, this is a ball, right? And it was a radius r. Okay. And for the ball, in calculus 1, we get a formula for the area circle, which is pi r squared. Now in calculus 3, we can get a formula for the volume of the ball and even maybe surface area. So the volume of the ball is going to be the 4 pi over 3 r cubed. Okay, and we're going to prove this formula. Okay, how do I do that? I just needed to figure out the volume of upper hemisphere. Okay, the volume of upper hemisphere. So the volume of upper hemisphere, we call it upper hemisphere ball, yeah. Usually the ball means it's a solid, the sphere means the surface. Okay, so this is going to be z equals, if we put in the xy coordinate system, this will be, the surface will be square of r squared minus x squared minus y squared. Okay, so this is a d, right? So the volume of the ball is twice of this double integral of the function. Okay, so basically we're going to evaluate this. You see, the double integral of this function is going to be the volume of the region under that graph, under the graph of that function, right? And above the its domain in the xy plane. Okay. So first of all, you write on that. The next step is trying to evaluate this double integral. Now use a tradition method. If we use a tradition method, right, you get x squared plus y squared equals r squared. That's a circle. Now how do you do that, right? It's challenging. Yeah. So it's not easy, but we can write down the iterative integral, okay? We can write down the iterative integral, okay? But maybe we're not able to solve it, okay? So we can do is, so I can use, let's use a two versions, okay? So this is in the XY plane, two different orders, okay? If we choose, this is negative r is positive. If we fix an arbitrary x, then yeah, for first version, fix fix an x, right? Between negative r and positive. Then the y value has upper bound and lower bound. The y value is going to be less than or equal to r squared minus x squared, rather than negative r squared minus x squared, right? So you have to negative r here, put a positive r, and that is going to be dx, right? And that will be dy, and the y is going to be from negative. You see? You have to evaluate this integral. I think it's complicated. Okay? I don't know how to do it, right? Yeah, it's complicated. You probably can do that, but it's still use a substitution in one variable. Okay. Okay. So we stop here, but we can express it in the iterative integral. What I'm trying to do is I'm trying to find a map from here. Here's r, here's a theta. Okay. Okay. I use x is r cosine theta, y equals r sine theta. Okay. So I want to find this is a map actually. This is a map. Okay. It sends a point r and theta to a point x and y with coordinates and y. So the question is, what kind of r theta would be sent to the circle? But you notice that for the circle, x squared plus y squared is determined, inside the circle is determined by this inequality. Okay, now I'm confused with the same r here. So yeah, let's change it to capital R, okay? Because this is a fixed capital, yeah. Okay, let's go back to changing capital. I don't want to use the same R here. Yeah, this is actually the capital. All right, so we change everything here. So, but x squared plus y squared using the above, right? X squared plus y squared equals r squared. So that means there's no restriction on the theta. Actually, theta is going to be from 0 and to 2 pi. From 0 to 2 pi. R is just needed from 0 to capital. Okay, because this implies okay, R is positive and not negative. So this rectangle rectangular domain is mapped to, this is my D bar, okay, is mapped to the circle, okay, right? Okay, great. So in order to apply the above formula, we needed to calculate, this kind of derivative, okay? So this is already, we know that, right? It's going to be R. We did this before, okay? Right? Now, this double integral over this circle, okay, should be equal to the double integral over this rectangle. And here the function x will be r cosine theta. y will be r sine square theta, and here's r. Okay, and then that'll be the above, but the above is r actually is dr d theta. Okay, so now you can use a iterative integral. You can use any form. Okay, because your domain right now is a rectangle. Okay, so this can be written from 0 to 2 pi and d theta, and here from 0 to capital R. After you simplify, this is going to be just r squared. Okay, another version is you can also from 0 to r, dr, and then that will be from 0 to 2 pi. And that's the same here, r squared minus r squared and r d theta. I think it doesn't matter which one is first. In this case, the second one, it's okay. You know, you can get rid of a theta first because this is a constant independent of, it's just 2 pi, right? And here's r squared minus r d. Yeah. Okay. Now you can use a standard substitution.
Gotcha.
Yes.
How do we know which one to choose first?
Well, doesn't matter. You know, you can write down both of them, and then if you look at the two iterative integrals, you find that one of them is easy to evaluate, then to choose that one. Okay, but sometimes if it's very hard to write down another iterative integral, okay, you can only write one of them. Then that's the only choice for you. Okay, so for me in this case, I just quickly write down the two. And fix a variable and determine the domain for other variable. Okay, and then because it's a rectangle, that doesn't matter which one first. But sometimes for the integral, you still find out one iterative integral will be. It's easy to evaluate one iterative integral, but it's very difficult to iterate the other one. Okay, so in this case, there's no difference. But for integrals in polar coordinates. The tradition method, yeah, well, tradition will be in this integral. Okay, theta will be outside. Yeah, because usually the theta is fixed. The domain for the theta is fixed. R can be changed. Okay. Anyway, so let's use substitution. Let's say let the t to be r squared minus r squared. So dt is going to be negative 2r dr. Okay. And this should be positive, right? How do you get, when I equals 0, you get square. When I equals r, you get 0, okay? So that is a t to the 1/2, and that will be I, and the dr will be negative 1/2 dt, okay? And now we are almost done, okay? Let's turn it around. So I get divided by 2 here, and then that's it. Okay. So the entire derivative of that function will be, okay, will be this. Okay. Evaluate at the 300 points. Okay. So let me check what's going on here. Yeah, I found out I have one number is missing. Okay, this is supposed to be 4 pi instead of 2 pi. But let me finish this first. Okay, that will be 2/3. Okay, and you plug in it's r squared then r to the 3/2 r squared, right? That's going to be just r cubed. Okay. So let's go back to see where we have problems. Okay. oh, I missed the 2 at the very beginning. Okay, I did not put the 2 twice here. The volume is going to be twice of that, right? So I just only calculate the integral. So that if I put the volume, and that is going to be, yeah, that is, I only evaluated this integral. Okay, so this is the integral of this part. Okay, so so the volume is going to be twice of this integral, right? Yeah, so twice of this integral. Okay, so it's twice pi 2 over 3 r cubed. So we end up with 4 pi over 3 r cubed. That's a formula for the volume. Okay, so we use a calculus, multivariate calculus. We can find out the volume. This is a good application of double integrals now using special point system. Okay. Okay. All right, let's take a look at another example. Okay. We're going to, let's take it from the book. Okay. Problem number 8. Okay. So this is double integral. This is over the double integral 2x minus y and dA. Okay, now how do we describe the d? Okay, d is the region, okay, in the first quadrant, okay, enclosed by the circle with radius 2 and the line y equals x. Okay, so we have to decide which way we're going to do. Okay, so this is a domain D. The circle. Okay. Okay, there are 2 different ways to set up this integral. Okay. First of all, let's set up let's express it an iterative integral for this. Okay. And maybe you're not able to evaluate it, right? This is there's the intersection point here. Intersection point will be, I think it will be square root 2 and the square root 2. Okay, when x equals y, yeah, this is it, yeah. Okay, and that means x is here, right? So I take an arbitrary point x and end up, look at the y value, right? So I'm not going to use polar coordinates right now. Set up an iterative integral for this. Okay, fix the x. Oops. Okay. Yeah, fix the x. Between 0 and the square root 2. And then can you, yeah. So let's determine the y value. Y, the top side, is going to be square root of 2 square minus x square, right? The bottom part is just x. Okay. So the iterative integral will be . we fix the x, so it's from 0 to square root 2. And the y is from x to the 2 square root, okay? That'll be 2x minus y dy, okay? Are we able to evaluate this integral? Possible, but it's a little bit complicated, okay? You can do that. The antiderivative of 2x minus 1 with respect to y, you will get square root, okay? You cannot get rid of square radical here, okay? So you can evaluate this integral, okay, without any trouble, okay? That's a little bit complicated. So what I'm trying to do is, yeah, let me show you one more step. So I just want to tell you, you can evaluate integral, okay? Antiderivative of this will be 2xy minus y squared, half of that, right? Okay. Then you plug it, okay? Minus 1/2. When you square it, it's 2 squared minus x squared. That's the first part. Then you plug it in x for y, so it's 2 squared. Okay. And I think this integral you can evaluate. Okay. So this is x squared. Okay. Now, if you simplify it, you will get, the only problem is this part, but this can use a substitution, okay, standard substitution. The rest of them just polynomial, just x squared and a constant, right? So, yeah, if you, let's simplify a little bit. And that would be 2x squared over 2 squared minus x squared. Then I have a minus 2, and I have a positive 1/2 minus 2 plus positive 1/2. So it's actually minus x squared. Okay. So this integral, everybody knows how to evaluate. Just a little bit complicated, okay? So I'm stopping here. So what we're trying to do is use our new method. Okay, so this is angle theta. Okay, so let's draw it here. Let's iron the theta, and the x is going to be r cosine theta, y equals r sine theta. To describe that region, I think I is going to be clearly between 0 and 2. Okay, right? And the theta is between pi of 4 and the pi of 2. So actually you get this rectangle is sent to that region, okay? Under that map. Okay, this is my d, that's d bar. Okay, so the integral of this d, x minus 2x minus y dA, now can be translated to the double integral of d bar. Okay, and here 2x is r cosine theta, y is r sine theta, then dA bar. So since our integral here, the d bar is a rectangle, so it doesn't matter which one is first. So you can either, the pi is theta is all side, so you will get, don't forget there's r here, okay, this comes from the derivative, okay. Okay, so that is from 0 to 2. 2r cosine theta minus r sine theta, and divide by. Okay. And or I think the second one is better. So I can get rid of the theta first. Theta first, yeah. Okay, so the question is the integral of a cosine theta. And what is the integral of sine theta? Okay, this is you can take a 2 r out, right? You can erase that. Okay, the r squared there. So the antiderivative of the antiderivative of 2 cosine theta minus sine theta will be 2 sine theta plus cosine theta, right? When you differentiate, you get 2 cosine theta minus sine theta. Okay, and there's r squared here outside. So evaluate the 2 endpoints. Okay, then you get 2, right? And here's the first one is 2 sine pi over 2. Cosine pi over 2 is going to be 0. Minus 2 sine pi over 4 plus, yeah. Right? So the first term here is just 2. Okay. Now the second one here, this is going to be 2 square root 2 over 2 plus square root 2 over 2. So you have a 3 square root 2 over 2. Okay. And this is just a constant. Okay. So then the antiderivative r squared is r cubed, 1/3 of r cubed. So you can combine them. It's 1 over this, right? R cubed. Okay. So finally, you get a very strange number, and that will be 2q over 3. Okay. You can simplify a little bit, yeah. So so you can get 2 cancel out. You get 4 minus 3 square root over 2 divided by 3. Okay, that's our answer. Yeah, that's correct answer. Okay. Right. I think I use polar coordinates. Much simpler. Now, sometimes the domain itself is already described in the polar coordinates. Okay. And yeah, let me give you an example. Okay. Use a double integral . Let me give you an example, good example. Okay, let's do this one. Okay, that's problem number 22. Find the volume of the solid, okay, inside the sphere, right, and outside the cylinder. X squared plus y squared equals 4. All right, first of all, I have to sketch the graph. Okay? Otherwise, it's harder to understand. Okay, this is my picture. Okay, so it's a ball, so you have to draw like that. Okay, it has a radius of 4, so this will be 4, and here be 4, right? That's on the top every 4. The cylinder will pass through this ball, okay? Because the circle on the XY plane will be just this. So you draw the cylinder. Okay, it's not easy to draw it. It's passing through this. Okay, I hope I learned some drawing skill. But this is a cylinder, right? You can see that. All right, what do we want to do? Have to be all side. Well, if you want to, it's inside. Let's try to find this. Okay, all side the cylinder. If you're able to find the volume of this piece, the cylinder, inside the cylinder. Okay, but also inside the sphere. Okay, I change the word a little bit. If you find this one, you can use a subtraction. Right, you can use a subtraction. Subtractions get to the area of the other side. Okay, all sides of the cylinder, right? So I'm going to change the word.
I thought we were trying. Oh, you're just changing it because I thought the question was.
Yeah, I can change it because I just take a difference. Make it easier. Yeah. So
the question is changing to find the volume of the solid inside the sphere and inside the cylinder.
Actually, the cylinder I show you the picture already, right? So this is because once you find this one, then you can use you already know the volume of the ball, right? So you minus the volume of this cylinder, then you get the volume of the remaining region. Okay. All right, let's set up the integral for this. Okay. So the disk here is D. D is going to be x and y, x squared plus y squared is less than 4. Okay. To find the volume, right? To find the volume, you just need to evaluate the integral of this. So this is a graph that piece. Okay, that piece is going to be the graph of this function. Okay. Yeah, it's very similar to the one we did for the volume of the ball. Okay, this is a graph. Okay, so this volume is going to be the double integral, but you have to multiply by 2 because this double integral only gives the volume under the sphere. Okay, above the D. Okay, so this is just 16 minus x squared minus y squared and dA. Okay, so that is what we want to do. We evaluate this integral over the disk. Once you set up this double integral for the volume, the next part is just focus on this double integral, right? Yeah, forget this 3D picture. So this is a disk. This is a D. Here's 2. Okay, to describe this disk using polar coordinates. Okay, all you need is here's a theta. I think theta should be between 0 and 2 pi. I is between 0 and 2 because an arbitrary point here, right, can be described by I and theta. So theta is between 0 and 2 pi, and I is between 0 and 2. Okay, So you will get you'll get a rectangular domain. Okay. So now the volume is going to be twice. Right. I'm going to change it to d bar. Okay. So that will be square root of 16 minus r x squared y squared, and here dr d bar. Okay. Okay. Then you can change this double integral on the rectangular domain to an iterative integral. Okay. To an iterative integral, you can use the traditional way to do. Yeah, I can use theta being outside. Oh, doesn't matter which order. Okay. So you can you can begin with r, right? So from 0 to 2, fix it. Then theta is between 0 and 2 pi. Okay, this is r d theta and then dr. Okay. After simplifying, this is going to be r squared. So now it's independent of theta. So you get 2 pi times this number. So you totally have a 4 pi. Okay, it's very simple. Okay, we get user substitution. Let s to be 16 minus t squared. So ds is going to be 2r dr. It's from when I is 0, and that's 16. When I equals 2, that is 4. That's going to be 12. Okay, that's s to the 1/2. R dr will be negative 1/2 dt at ds. Okay, so here's negative sign there, so you can turn this around. So from 12 to 16, and I'll have to take 1/2 out. Okay, so s to the 1/2 ds. Okay, so the antiderivative of this will be so my answer here is a 4 pi over 3. Okay, and 16 to the 3 over 2 minus 3 to the 3 over 2. Okay, so this is the answer. Okay, I'm not able to even simplify. We can simplify a little bit. Okay, so 4 pi over 3, 16 is going to be, 16 3 over 2, 3 to the 3 over 2 is going to be 4 squared to the 3 over 2. So it will be 4 cubed. Okay, 4 cubed. Okay, 4 cubed is 16 and 60. I think it's 64. 16 times 4. Yeah. And 12, we're not that lucky. Okay, and that is going to be 12 to the 1 and to the 1 times 12 to the 1/2. That's 12. It's a square of 12 is 2 square of 3, so it's 24 square of 3. Okay, so 64 minus 24 square of 3. This is our solution. Okay. Now, the byproduct. Okay. The byproduct is if you have a ball, right? And what I'm going to do is I'm going to cut a small piece. I put it here. If I know the radius is going to be, this is in the ball, I, capital I equals 4. So if this is a 2, so what is the volume of that? Now you can calculate by take the difference, because you already know how to calculate the cylinder, right? The area, the volume of cylinder, the minus this part. See, this is going to be the whole part, right? Add this part, right? So, but you know how to find the cylinder, okay? You know how to find the cylinder. So that's a whole, this, we find the volume of this already, right? Then you subtract the volume of cylinder, you get that, okay? All right, so this is how do we solve the problem using color coordinates. Right. Sometimes we are let's try this. Okay, that's problem number 32. We are not given the domain. We are given.
I'm sorry, Professor. I'm still stuck on this earlier problem before we jump on to the next one.
Okay.
So we found the volume of that weird little cap piece, the R equals 2, right?
Yeah.
But is that what answered the question, right?
So answer to this question is we get the volume of this piece as let me call it.
Uh-huh.
Yeah. We get the volume of this, right?
So we would need to add the volume.
Yeah, first we find the volume
to our answer to be able. So I could just say the answer that we got, which was like 4 pi thirds, blah 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 blah, and I could just say plus the volume of the cylinder, right?
No, I actually want you to find the volume of this piece. Yeah. So what is the volume of that piece cut from the sphere?
Right.
Yeah, cut
that
from
doesn't
the
answer
sphere.
The question, right?
Yeah, if you already know the volume of this larger one, okay, the volume of this larger one will be divided by 2. So 2 pi over 3, 64, 24 square 3, because it's only half of that. Okay. Yeah. And then the volume of that cylinder, okay, you have to figure out the height, okay. So this is a 2. What is the height? Okay, the height is here's a 4. Okay, so it's going to be 16 minus, it's a square root of 12. This is the height. Okay, so the cylinder of this cylinder is going to be the base area times the height. Okay, this by the Pythagorean theory, you get square root of 12, because 16 minus 4 square minus 2 square is 12, 12 square root of 12. So it's going to be 2 square root of 3. Okay, so this is the 8 pi square root of 3. So the volume of this piece, okay, is going to be the difference of those two numbers. Okay. Yeah, use a subtraction. You can get the volume of the head, the top, right? All right. Yeah. Yes, the difference gives you the volume of that piece. Is going to be the volume. It's going to be 2 pi over 3, 64 minus 24 square 3 minus 8 pi square 3. Okay, and after simplifying, we get an answer.
Thank you.
Okay. I'm not going to work on the problem 32 directly, but I'm trying to give you this first. So it's from 0, and that will be 4 minus x squared, square x squared plus y squared, dy and dx. Okay. Evaluate this iterative integral. Now you can do that, right? It's very hard to evaluate this iterative integral. The reason is it's a square root of x squared plus y squared. So with respect to y, how to find the antiderivative of square root of x squared plus y squared, right? So we should figure out the domain D. For the domain D, how do you figure it out? Okay, for an x between 0 and 2, we know that y is between 0 and 4 minus x squared. So take a look at y. If we consider this equality, you end up with, you get x squared plus y squared equals 4, which is 2 squared. So now we have a pretty good idea to evaluate, to describe the domain. Okay, this is y-axis. So x is from 0 to 2. But y is going to be between 0 and the square of 4 minus x squared. So actually you're looking for, you find this is a domain D. Okay, just the first quadrant, in the first quadrant, the third quadrant, in the first quadrant. Okay, so this is a D. Then this is reverse process. Then this double integral, okay, is nothing but this is this double integral over that D. Then you have a freedom to go which way go, right? It's a nice sector. So you can use other methods to use evaluating this double integral. In other words, you are going to use a polar coordinate. You use a substitution, special substitution for this integral in two variables. Okay, so you can simply write down, so you can describe this D, right? Let's describe D and let's draw the picture here, okay? When you do the homework, I hope you draw the picture. That's a D. Okay, and then in the middle, I have R cosine theta, Y equals R sine theta. Okay. Then I have to figure out what is the value for the R, what is the value for the theta. I think I pick up arbitrary point here, the theta, clearly theta is between 0 and pi over 2. And R is between 0 and 2. So you get a rectangular domain. That's great. So R is between 0 and 2, theta is between 0 and pi over 2. Okay. Then that double integral becomes the double integral on this rectangular. Okay. And x squared is going to be R cosine theta squared. R sine theta squared. Then we have R dA. And don't forget this R here. Don't forget this R. Okay. So this is a much simpler. Okay. You will see that. So this is a square, R squared. So square R squared is R. So it's going to be R squared dA. Okay. Thereby. Now, this is the integral over the rectangle. So it's the integral from 0 to pi over 2, and from 0 to 2, and R squared dr and d theta, right? Yeah. Then the antiderivative of that is 1/3 R cubed, and I'm going to get 2 cubed over 3. And this is a constant, right? And then the integral from 0 to pi over 2 d theta, and you get pi over 2. So 2 cubed over 3 and pi over 2. Okay, and you simplify it, you will get 4 pi over 3. Okay, 4 pi over 3 is the answer. Okay. And without using polar coordinates, without using substitution, we call it substituting 2 dimensional. Then it's very difficult to evaluate that integral. Triple integral, iterative integral, yeah, iterative integral. Okay, now I'm going to I'm going to do a slightly different problem. That's a problem number 32. Okay, evaluate this, evaluate this iterative integral. For the same reason, we are not able to evaluate this integral. It's very complicated, right? The only difference is here, this part. Okay, I make a slight change. So this will become a double integral of that function. Now we have to figure out what is the domain. Okay, right? So fix, so x is all sides, so fix x between 0 and 2. Let's determine the y. Okay, y is between 0 and 2x minus x squared, right? So let's draw the picture here. For every x between x, y is between, you have one piece like that, okay? So the top one, y is going to be square root of 2x minus x squared. Now I have to make sure 2x minus x squared is positive, okay? The reason is, okay, so this is, otherwise there are some problems there. X cannot be arbitrary. So 2x minus x squared is going to be x, it's positive, right? 2 minus x. So you see, when x between 0 and 2, x is positive, or this, right? 2 minus x is positive. So this is a fine, this is a positive. So that's why I can talk about square root. Square root 2x minus x squared. So when x changes from 0 to 2, the top point of this line segment changes. So what kind of orbit you're going to get, right? So you consider this is the same as y squared equals 2x minus x squared. Okay. So I get x squared plus minus 2x plus y squared equals 0. I'm going to add 1 to each side. So this will be x minus 1 squared plus y squared equals 1 squared. So this is circle at the center 1 and 0. So this is the same circle. Okay, this is a circle. Okay, this actually gives you a circle. Now we are in trouble. How can I use a coordinate? So this is a domain. Okay. Yeah, this is a domain D. So now we have let's go back here. This is a domain D. Okay. It's going to be x minus 1 squared plus y squared equals 1 squared, and y is going to be positive. Okay. So this is my D. I want to use a polar coordinate. Okay. I want to use a polar coordinate. So this is a point. Okay. That's a theta. I think theta starts from 0 to pi over 2. Okay, how can I describe this? I want to describe the R here, okay, the upper bound, right? So what I'm doing is I use this equation, okay, it doesn't matter, okay? So x equals r cosine theta, y equals r sine theta. So I plug into our equation, have r cosine theta squared minus 2r cosine theta plus r sine theta squared equals 0. So those two gives you r squared. Okay. All right, so now you have r minus 2 cosine theta equals 0. So you have two solutions, r equals 0, that gives this point, r equals 2 cosine theta. So the largest possible value for fixed theta, r is between 0 and the 2 cosine theta. So fixed theta between 0 and pi over 2. R is between 0 and 2 cosine theta. Okay, cosine theta, yeah. Okay, so now it's pretty clear, right? So what kind of a domain for the d bar? Here's R, here's a theta. This is a pi over 2. Okay, when theta equals 0, R is 2. And when theta increases to pi over 2, R is going to be 0. So it's going to be something like that. Right? And that's okay. That's better than the above one. Okay. For the fixed theta, okay, where the line goes, okay, think about it. This red line, okay, is mapped to here. Okay. Okay, so when you lift the line from bottom to the top, then you get all the line segments here. Okay, so you have another one. Let's choose a different color. Yeah, if we have another one here, let me. No, I don't have other colors. Yeah, so this is another one. That'll be here. Okay. All right, so now we're going to convert this integral on D to the integral on D bar. So where's my original integral? I forgot. Okay, just square root x squared plus 1 squared. Okay. So this double integral, okay, it becomes this integral over here. And here I ask x squared plus y squared, just r squared. Okay, and don't forget the r here, the a bar. Okay, now now we have to use which I think we should put pi outside, theta outside, and for each theta, right? I is from 0 to 2 cosine theta, and here's r. You get r, right? R squared. So d r. Right. Yeah. So now I get antiderivative. It's from 0 to 2 cosine theta. Okay. And actually I get 2 cubed 8 over 3. So we end up with this. Question is how to evaluate this integral. Okay, some of you still may remember. That was a long time ago, right? So we got 8 over 3. I think it's going to be cosine square theta. That's 1 minus sine square theta and cosine theta d theta. If you can express in that form, yeah, this is a cosine square theta. Then you get cosine cubed, right? Then you have to use a substitution again. Okay, you let u to be sine theta. So du equals cosine theta. Okay. So when theta is 0, it's a 0. When theta is pi over 2, that's a 1. It's 1 minus u squared, and the theta d cosine theta, yeah, the theta is du. Okay, great. That's another substitution. See, we use a lot of substitution here. the antiderivative will be u minus 1/3 u cubed. Okay. When you plug in 1 for u, you get 1 minus 1/3. Okay. I get 2/3. Okay. So that will be 16/9. Okay, finally we get this. I don't have a time to find another problem, only a couple minutes left. But this example shows you, okay, if we are given an iterative integral, and you may be not able to solve it. But you look at the domain of the iterative integral, you find out it's possible can convert the integral to an integral in polar coordinates, especially, yeah, it's like a domain looks like a circle, a portion of a circle, okay? Then if you do not use a polar coordinate, it involves its radicals. That's very complicated, okay? So this is the example I've discussed. So on the test, if I give you a problem iterative integral evaluate, they have to think about should I continue or without the changes of coordinates. Okay. Sometimes maybe you can use a polar coordinates to evaluate and it can quickly solve the problem.